FlashAttention-T towards fully tensorized attention by exploiting Tensor-Vector Parallelism. That is the paper we are breaking down today. It's coming out of PPOP 26 from Jianxing and his colleagues. And if you are building or serving LLMs, you really need to pay attention because your H100s might be wasting, nearly 40% of their compute cycle just doing nothing.
It sounds like an exaggeration, but it's a hardware reality. We call it the vector interval. I mean, modern GPUs have these massive, powerful tensor cores for matrix multiplication, right?
Yeah.
But the softmax operation, which is the heart of attention, that still runs on the slower vector or CUDA cores. So the tensor cores finish their GM almost instantly and then just sit there. They sit idle, waiting for the vector unit to catch up. On a Hopper H100, that idle time can be up to 36% of your iteration cycles.
Which is just a massive inefficiency. But this paper, FlashAttention-T, it proposes a solution. Essentially, they force the tensor cores to do the softmax work. They do this by repurposing matrix multiply add instructions to handle scalar operations.
And it works. I mean, it really works. They reduce that vector interval down to just 2.7% on H100s. And they're getting speedups of up to 1.17x over FlashAttention 2 and 3. And they validate it on models like Llama 3 and Qwen without losing any accuracy.
All right, welcome to our AI paper podcast. Let's get into the weeds on this one. We threw some pretty heavy numbers out there just now, but I want to understand the root cause here. I mean, we all know flash attention is the gold standard. Tri-DAO's work is legendary. FlashAttention 2 and 3 are, masterpieces of engineering. So why are we even seeing a 40% idle time? Is the hardware just that unbalanced?
It is exactly that unbalanced. It's a classic case of the hardware evolution just outpacing the algorithm. Think about the standard attention mechanism. It's like a sandwich. You have two huge general matrix, multiplies GMs. You have Q times K transpose, and then later P times V.
Right. And tensor cores exist pretty much solely to crush those GMMs.
Exactly. They are the Ferraris of the chip. But sandwiched right between those two high-speed runs is the softmax.
Yeah.
You have to take all the logits, you exponentiate them, you sum them, you normalize them. Traditionally, that is all element-wise scalar math. And scalar math lives on the vector core.
The CUDA cores, the sedans of the chip.
Right. So the tensor core blasts through that first GMM, hits a wall, and just has to stop. It literally sits there in what the paper calls the vector interval, just waiting for the vector core to finish all the softmax math before it can even start the second GMM.
And looking at the specs from the paper, this gap is actually getting wider.
Oh, significantly.
Yep.
From the Ampere architecture, so the A100s to Hopper, the H100s, the tensor cores got exponentially faster. But the vector units, they didn't get that same boost. So that waiting room time just increased. The paper points out that with a head dimension of 64, which is pretty standard for models like Goody-Goody-RC, the idle time on an H100 is 42%.
42%. That means for nearly half of every cycle, the part of the chip you paid the most money for is just sitting idle. So the whole premise of FlashAttention-T is basically stop waiting for the vector core, make the tensor core do the softmax.
Precisely.
But that sounds like a square peg in a round hole, right? Tensor cores do one thing, matrix multiply add, D equals A times B plus C. Softmax is scaling and summation. You can't just tell a matrix unit to divide everything by 5.
Well, you can't tell it to divide, but you can sort of trick it into scaling. And this is the first really big hack in the paper. They repurpose the MMA instruction. Let's say you want to scale a matrix A by some factor, call it alpha. The tensor core has no idea how to do that.
Yeah.
But if you set matrix C to 0 and you construct a very, very specific matrix B.
You essentially turn the multiplication operation into a scaling operation.
Conceptually, yes.
Yeah.
You create this kind of dummy multiplication where the result is mathematically equivalent to just scaling A by alpha.
Okay, but I'm going to stop you there because I've looked at the PTX documentation for tensor cores. They aren't simple grids. They use swizzling and these complex internal layouts to optimize the electrical pathways. So if I just feed a dummy identity matrix into B, the output isn't going to be a clean matrix. It's going to be permuted. The data will be all scrambled.
You are absolutely right, and that is the catch. The hardware output comes out in a specific permuted order that depends on the instruction, in this case, HMMA.1688.F32.TF32. And if you tried to unscramble that using standard register moves, the overhead would just kill your performance gain. You'd be right back where you started.
So you have the right numbers, but they're all in the wrong places. How do they fix that without slowing everything down?
They turned it into a discrete optimization problem. They used something called Cayley distance.
Cayley distance? I have not heard that term since a graph theory class.
Okay.
Walk us through why that applies here.
So, Cayley distance measures the minimum number of swaps you need to make to transform one permutation into another. Think of it like a Rubik's Cube or a scrambled alphabet. The authors analyzed the internal permutation groups of the tensor core itself. They asked, is there a specific way we can arrange the inputs in our dummy matrix B so that the output permutation has a minimal Cayley distance to the correct order?
So they aren't just looking for any matrix B that does the math. They're looking for the one golden matrix B that does the math and spits out the data in a format that's really easy to repair.
Exactly. They found these specific permutation matrices where the cost to fix the order is just negligible. And this allows them to use the tensor core for scaling without paying that huge penalty for the data scrambling.
That is incredibly clever. It's designing software that is literally aware of the silicon's physical routing.
It is. And they didn't stop at scaling. They also tensorized the row sum reduction.
That's the part of softmax where you sum up all the exponents to normalize them. Usually that's an all-reduce operation across threads, right?
Yes. In the standard vector world, all the threads have to talk to each other to sum up their values. That requires synchronization barriers. Stop, tell me your value, add it to mine. And barriers, as we know, kill parallelism.
And the tensor core gets around this.
The tensor core already shares data internally within the warp for its matrix multiplication.
Right.
By cleverly arranging the input matrices to be vectors of ones in just the right spots, the multiplication effectively becomes a summation across all the rows. They get the reduction almost for free without any explicit thread synchronization barriers.
Okay, so we have the hardware hacks, we can scale, and we can sum using the tensor core. But there's an algorithmic problem here that we really need to address. FlashAttention uses online softmax for numerical stability.
Right, and this is usually where the engineers start getting skeptical.
For a good reason. I mean, standard online softmax relies on finding the maximum value of a single row. You subtract that max from everything else so your exponents don't just blow up to infinity, either the x of. But the tensor core operates on tiles, on blocks of data. If you're using that matrix B hack for scaling, you are applying the exact same scaling factor to the entire tile. You can't reach inside the instruction and pluck out a different M for every single row.
You've hit the nail on the head. The hardware forces you to treat the entire block uniformly. You cannot use the row-specific max. So the authors introduce what they call the surrogate maximum, which they denote as M hat.
Then what is M hat exactly?
Instead of the max of just one row, they take the maximum value across the entire tile of rows, say 16 or 64 rows at once. And they use that one single global max to stabilize the whole block.
I can already hear the ML engineers screaming. If you use a global max for a block and say row A has a huge outlier like 50 and row B has small numbers like 0.1, well, when you subtract 50 from 0.1, you get meta to 49.9, and e to the negative 49.9 is basically 0. You're creating massive underflow in all the quieter rows.
That is the theoretical fear, absolutely. If you underflow to 0, the attention weights just vanish. You get 0 divided by 0 during normalization, and the model creates nans. Game over.
So, how do they justify taking that risk?
Well, they provide a pretty rigorous statistical proof. They modeled the attention scores using Gaussian distributions, and they calculated the probability of a catastrophic underflow, that is, where every single element in a row becomes 0 because of an outlier in a neighboring row.
Yeah, and what was the probability?
Statistically negligible. We're talking probability so incredibly low that they just don't manifest in typical training runs.
Statistically negligible is a very bold claim when you're training a trillion parameter model.
It is, but notice one key thing. M hat is always greater than or equal to the true max. That guarantees that x minus m hat is always negative or 0. So e to the x minus m hat is always less than or equal to 1.
Ah, so overflow is physically impossible.
Correct. The only risk is underflow. And they show that for real-world LLMs, Llama, Mistral, Quinn, the distribution of lotsits is such that you simply don't get that specific pathological case where one row kills all of its neighbors.
And they have a fallback, right, if the math detects some kind of crazy distribution.
Yes. If the values go out of bounds, the kernel can revert to the standard vector-based computation. But in all their benchmarking, they never once triggered the fallback.
Okay, so the math holds up. Now let's talk about implementation. Because this isn't just about changing an algorithm, it's about fitting it onto a specific architecture. And the paper makes a huge distinction between Ampere, the A100, and Hopper, the H100.
Yes, this is what I call the architecture war section of the paper. You cannot just write one kernel that's optimal for both.
Let's start with Ampere, the A100.
On Ampere, the strategy relies on ILP instruction level parallelism. The scheduler on Ampere is flexible enough that you can issue a tensor instruction, and while it's executing, which takes a few cycles, you can sneak in some vector instructions.
Interleaving them.
Exactly. They tested different ways to split up the matrix tiles to maximize this overlap, horizontal splits versus vertical splits. They found a 1-to-1 horizontal split was the sweet spot. It keeps both the tensor and the vector units busy within the same warp.
But then comes Hopper. The H100, it's asynchronous. It has thread-level parallelism, or TLP. With the new warp group MMA instructions, theoretically that should make things easier.
You would think so, but they ran into a major roadblock. The compiler. Specifically, the NVIDIA compiler, NVCC.
The compiler didn't like their hacks?
It hated them. On Hopper, the authors wanted to tensorize everything, the scaling, the reduction, the works. But when they tried to issue these asynchronous WGMMA instructions alongside their tensorized softmax, the compiler saw register dependencies.
Meaning instruction B needs the result from instruction A to run?
Right. And when NVCC sees that specific kind of dependency in this context, it just serializes the instructions. It forces them to run one after another to prevent any potential race conditions.
Which completely defeats the entire purpose of parallelism. You're back to waiting.
Exactly. The compiler was just being too conservative, so they had to compromise. On Hopper, they do not tensorize the scaling. They leave the scaling operation on the vector unit.
Wait, they leave the scaling on the slower core? That seems completely counterintuitive.
It's a strategic retreat. They only tensorize the row sum reduction, which is the final stage of softmax.
Why does that specific change help?
Because the reduction happens at the very end of the softmax block. By tensorizing only that reduction part, they can pipeline it into the next iteration's GMM.
Oh, I see. So while one warp group is doing the vector scaling for batch A, the tensor core is already starting the reduction for batch B from the previous step.
It's a little more nuanced, but that's the idea. It allows the vector softmax of one stage to overlap with the tensorized reduction of another stage. They're essentially hiding the vector work behind the massive tensor workload of the next step.
So on the A100, they weave instructions together with ILP. On H100, they overlap different pipeline stages across warp groups with TLP.
Exactly. It's a masterclass in architecture-aware scheduling. You really have to fight the compiler with the tools you're given.
Okay, let's get to the scoreboard. We've done the math. We've fought the compiler. What's the final payout?
The vector interval reduction is the headline. On the A100, the idle time drops by roughly 2x. But on the H100, it is just spectacular. That 36 to 40% idle time we talked about, it drops to 2.7%.
2.7%. They effectively just deleted the bottleneck.
They did. For all intents and purposes, the vector interval is gone. In terms of raw end-to-end throughput, this translates to a speedup of roughly 1.17x over FlashAttention-2 and 3.
1.17x. Now, to a layman, 17% sounds nice. But to an ML engineer who is managing a cluster of 5,000 H100s, 17% is tens of millions of dollars in compute time.
It is absolutely enormous. And remember, FlashAttention is already one of the most optimized kernels in existence. TriDAO and the NVIDIA team have optimized the hell out of it. Finding another 17% on top of that is it's like finding a new gear in a Formula One car that everyone thought was completely maxed out.
And the speedup is even better on smaller head dimensions, right?
Yes. For a head dimension of 64 or 128, which are common in models like Qwen or some of the older GPT architectures, the gains are highest because that's where the vector bottleneck was most severe to begin with.
We touched on the theoretical accuracy with the Surrogate Max. Did they actually verify this on real model checkpoints?
They did. They ran Llama 3.8b, Mistral 7b, and Qwen. They evaluated using PassAt-10 on human evil and the standard MMLU benchmarks.
And the verdict?
Statistically identical to the baseline. Zero degradation in model performance.
They also ran those synthetic stress tests, which I found really interesting. They deliberately generated random attention scores with a high variance to specifically try and break that underflow assumption.
Right. They wanted to see the error. On the A100, the root mean square error, the RMSE, was around 10 to the minus 3. On the H100, because they only tensorize the reduction and keep the scaling on the vector unit, the error was even lower, 10 to the minus 7.
10 to minus 7? That's effectively 0 for floating point operations.
It is. It confirms that the surrogate maximum is a perfectly safe optimization for this domain.
So, FlashAttention-T. It's faster, it's accurate, and it better utilizes the hardware we've already paid for. What's the broader implication here?
I think it signals a real shift in how we view the GPU. For years, we've treated tensor cores as these fixed function units. Here's your matrix multiply unit. Use it for that. This paper argues that if you are willing to get your hands dirty with the instruction set and handle things like Cayley distances, these are actually general-purpose parallel math units.
You're repurposing the silicon itself.
You are. And looking ahead, this problem isn't going away. We're moving to FP8. We're looking at Blackwell. Tensor cores are only getting faster and faster. That gap between tensor speed and vector speed is just going to keep widening.
So relying on the vector unit for softmax is basically a dead end.
It certainly seems like it. It really raises a question for the hardware architects. Will future GPUs abandon the vector unit entirely for attention? Or maybe we'll see a dedicated softmax unit built into the silicon.
Or maybe we just change the algorithm to get rid of softmax altogether.
That's the holy grail, isn't it? Linear attention. But until that day comes, we have to deal with the exponential.
Well, if you're listening and you want to see the specific permutation matrices for yourself, or if you just want to appreciate the math behind minimizing Cayley distance, I highly recommend you check out the paper. It is a fantastic example of deep, low-level optimization.
Absolutely. FlashAttention-T. Definitely worth the read.
And that's it for this breakdown. Thanks for tuning into the podcast. We'll see you next time.
Happy trading.